Welcome to the Explainer. Today we're diving deep into the tech that's behind, well, pretty much everything you're hearing about in AI. From ChatGPT to mind-blowing scientific discoveries, it's all powered by one thing, the transformer architecture. This is the engine that really kicked off the AI revolution as we know it. I mean, have you ever really stopped to think about it? How does an AI write a poem that actually makes you feel something? Or spit out working code for a website? It honestly feels like magic. But it's not. It's all about understanding language in a completely new and profound way. And yeah, the answer to that question, the absolute core of almost every big AI breakthrough lately, is an architecture with a name that sounds like it's straight out of a movie, the Transformer. So let's pull back the curtain and see how this thing actually works. Okay, first things first. Before we get into the heavy stuff, we have to understand something really basic. How does a machine, which only gets numbers, learn to read something like English? See, computers don't get the subtleties of human language. They don't speak English or Spanish or Mandarin. Their native tongue is math. So the very first job for any language AI is to be a translator, turning our words into numbers that it can actually work with. And this translation, it happens in this really clever three-step process. First, we have to chop the sentence up into pieces, which is called tokenization. Then we give each of those little pieces a deep numerical meaning through something called embeddings. And finally, we have to make sure the model knows the order of the words by adding a sense of position. So let's start with tokenization. The easiest way to think about this is like building a dictionary. We take a sentence, we break it down into words or even parts of words, and we give each unique piece its own ID number. So I becomes 0, love becomes 1, cats becomes 2, and you get the idea. It's a simple but absolutely essential first step. But, a simple ID number isn't nearly enough to capture what a word actually means. That's where embeddings come in. Each one of those token IDs gets mapped to a long list of numbers. We call it a vector. And this isn't just a random list. It's like a rich numerical fingerprint that captures the word's meaning and how it relates to all the other words. But here's where we hit a snag. A pile of words isn't a sentence, right? Just look at these two examples. They use the exact same words, but the order totally flips the meaning. A model that just looks at the words themselves wouldn't have a clue who's chasing who. So how do we fix that? We fix it with something called positional encoding. And this is genius. Think of it like giving each word's numerical fingerprint its own unique GPS coordinate. By adding this position info right into the vector, the model now knows not just what a word is, but exactly where it is in the sentence. And this little trick is what lets transformers process every word at once, in parallel, without losing the all-important context of word order. All right, so the model can read our words, and it knows what order they're in. Now we get to the part that truly made transformers a game changer. How they understand deep context. This is the secret sauce. It's all done through this incredible mechanism called self-attention. And the idea is just so powerful. For every single word the model looks at, it can also look at all the other words in the sentence and decide, okay, which of you are the most important for understanding this word right here. It literally learns to pay attention to the right context. A really great way to get your head around this is to think about a web search. The word the model is currently focused on, that's the query. It's your search term. The model then compares that query to the key of every other word in the sentence. Think of keys as the titles of all the web pages out there. When it finds a really good match, it pulls that word's value, which is like the actual content on the web page, to get a richer understanding. And here's the kicker. The model doesn't just do this once. It runs this whole search process at the same time across lots of different attention heads. You can think of it like a whole team of research specialists working together. One head might be tracking grammar, while another is figuring out who did what to whom. This multi-headed approach is what gives the model such a rich, layered understanding of the text, all in a flash. Now, for a long time, the motto in the world of AI was super simple. Bigger models plus more data equals better results. But as it turns out, the story is, well, it's a little more complicated than that. This right here was the conventional wisdom. It was the rule book everyone was playing by. The basic idea was that if you just keep making your model bigger and feeding it more and more data, its performance will just keep getting better and better forever. It was the bigger is better era. But then, researchers started noticing something a little weird. Take a look at these charts. They show the model's loss. Just think of that as its error rate. Lower is better. On the left, with 5 billion bits of training data, the loss drops perfectly as the model gets bigger, just like the theory says. But now look at the chart on the right. At 500 billion bits of data, the real performance, those black X's, starts falling behind the predicted red line. The improvements are slowing down. They call this phenomenon subscaling. And this isn't just theoretical stuff in a lab. Let's look at a real-world example with the famous Llama models. This chart clearly shows that the performance jump you get from Llama 2 to Llama 3 starts to flatten out, even though the cost to train it is going through the roof. We're hitting a wall of diminishing returns. Which, of course, brings up a huge question. Why is this happening? If just throwing more data and bigger models at the problem isn't the whole answer anymore, what are we missing? What's causing this slowdown? Well, the answer, and really the future of where AI is headed, seems to be less about scaling bigger and more about scaling smarter. It turns out the main culprit seems to be something called data density. It's basically a measure of your data's quality. If your data has high density, it means it's packed with a lot of redundant or super similar information, which surprisingly can actually hold a model back. You can see it on this chart. High-density data makes performance hit a plateau. Think about it like this. It's like trying to teach a student about calculus by giving them 10 different textbooks that all explain it in pretty much the same way. After the first book, the rest don't really add much new knowledge. You'd be way better off giving them a book about physics instead. And that's really the heart of the matter. After a certain point, just piling on more data doesn't lead to more learning if that data is just rehashing the same old stuff. For a model to keep getting smarter, it needs new, diverse information. Quality and variety are starting to beat pure quantity. So the key thing to take away from all this is that the frontier of AI is shifting right now. The race isn't just about who can build the biggest model and hoard the most data anymore. It's becoming a race to find the highest quality, most diverse data, and to figure out more efficient ways to learn from it. It's about being smart, not just big. Which leaves us all with one final thought to chew on. As we push forward, is the next great AI leap going to come from the team that builds the biggest digital brain, or from the team that finds the smartest information to feed it?